Assalamu alaikum warahmatullahi wabarakatuh. We are just going to discuss the series solution. We already done in the last lecture and we have 5 parts for that one. And we discussed power series solution. That's how we can use the power series for finding the solution of the differential equation. Any type of differential equation. There is no, mostly we are taking second order differential equation for that one. Now today we are going to discuss here, we are having this linear differential equation a2x plus d2y by dx squared plus a1x dy by dx plus a0xy equal to 0. The first method we discussed, as I mentioned, that is the power series method. And this power series method, we are discussing the solution about ordinary point. There we have seen that we are having a2 of x equal to 0. We take a2 of x and we take the point x equal to x0 if a2 of x at x, we say here point x0, at point x equal to x0 is equal to 0. When you say the point is, then this is our singular point. We say this point is a singular point. And if we are having here the case number 2, if we are having a2 of function at x equal to 0 is not equal to 0 at the point x0, then here this point x equal to x0 is singular point, and here this point x equal to x0 is ordinary point. And we have this discussed our solutions about the ordinary points. So it's very interesting, and we have not said that we are not going to discuss solution about the singular point. Now we are having the second method. In second method we say we are having Frobenius method and we find the series solution. We can write here the series solutions, also here series solutions of our problem about the regular singular point. It means we are going to distinguish between a singular point, one as a regular singular point and other as irregular singular point. I normalize my equation. I get here d2y by dx squared plus we divide by a2 of x to normalize. We get here a1 of x over a2 of x dy by dx, and we have plus a0 of x over a2 of x y, and that we say is equal to 0, and we just rewrite them. We say we can write as d2y by dx squared plus px dy by dx, and we having here plus qx y equal to 0, where my p of x is this coefficient of dy by dx, that is a1 of x over a2 of x, and we having here q of x. Q of x is equal to a0 of x over a1 of x. What I said about the ordinary point, you can see it here. Our denominator must not be 0. Here a2 of x. Here we are having a2 of x. This must not be 0. When this is 0, then the point is singular point. It means we are having the point, when say the singular point, where this is 0. Now we take this case and we are going to develop here this function. We say we are discussing the point x equal to x0. Now we are going to multiply this p of x with x minus x0, p of x, and multiply the function q of x with x minus x0, p of x, q of x. Now we will check these two. If these two are analytic, both, then we say that point x equal to x0 is a regular singular point, is regular singular point. And if this is not the case, they are not analytic. We have seen the analytic, that the function can be described, the function we say it is analytic, we say it must be described in the Taylor series. And we say these factors, it means these factors are defined. When they are continuous differentiable in case of analytic, but the minimum thing is that they are defined. If they are defined, then we say that they are analytical and the point is regular singular point. Now we are in position to define the regular singular point for the differential equation. As I said, it's a linear differential equation, second order. And we are having here, we take the point x equal to x0. We take this point and check is it regular or irregular singular point. This means when x equal to 0 mean here This means we're having a2 of x0 is equal to 0. If it is not equal to 0, that we have seen this will be an ordinary point. If this at this point a2 of x0 is not equal to 0, ordinary point, x0 then it's a singular point. So it's a singular point, this point. I want to see is regular or irregular. So we multiply by x minus x0 to px and x minus x0 square to qx. Now we look on these functions and say, are these analytic at the point x equal to x0? If they are analytic, then we say this is a regular singular point. And if they are not analytic, we say it's irregular singular point. Whenever it's the analytic, analytic number one as say is the function that we can write in terms of Taylor series. If we are having here the polynomial function as the result, then every polynomial function is analytic at every point. And if it's a rational function, that means rational function is like the function here f of x over g of x, where g of x is not equal to 0, we say it's a rational function. So this is analytic at all the points where it is defined. So these are the, so mainly we are saying where the function is defined, then we say the function is analytic, and that point will be, if these two conditions are hold, then this is a irregular singular point and regular singular point. For the regular singular point, both conditions must be satisfied. If any one of the conditions is not satisfied, it will become regular. For example, it's analytic but not analytic at this point, so it will be not regular. Or it is analytic here but not analytic here, it's not defined here, then we say it's also a regular singular point. If it's analytic here, also here, then we say it's a regular singular point. I will show you with the help of example. So I give you the example. We're having here the example to classify the singular points of the differential equation. Step one is, first we find what are the singular points. So we are having here a2 of x is equal to 2x squared. Now singular points are where the value of a2 of x is equal to 0. We say a2 of x is equal to 0. This means 2x squared equal to 0, and this may give me the value of x equal to 0. So we say x equal to 0 is singular point. Step 2 is, we want to find is a regular singular point or irregular singular point. We need to find px and qx. I divide by 2x, and normalize the equation, I get d2y by dx squared minus x over 2x squared dy by dx. Then we're having here plus x minus 5 over 2x squared y equal to 0. I can identify my p of x. My p of x is equal to minus 1 over 2x. Here x is cancelled with x and get 1 over 2x. And my q of x is equal to x minus 5 over 2x squared. So this is my q of x. Now we can see it here. When we want to find the regular, irregular singular point, then we multiply our values by x minus x0 to p of x and x minus x0 whole square by q of x. My x0 is 0, so I multiply here x p of x with x. So I get here x p of x is equal to, we have here x into minus 1 over 2 of x is equal to minus 1 by 2, that's the constant. Then multiply q of x by x squared. So get x squared q of x is equal to x squared into x minus 5 over 2x squared, and I simplify, I get 1 by 2 x minus 5. Now this x minus x into p of x, this analytic function is defined at x equal to 0, and x squared q of x also analytic function is defined at x equal to 0. So we say x p of x and x squared q of x are analytic, you can say is defined at x equal to 0. This implies x equal to 0 is regular singular point. And if this was not analytic or not defined, we say this is not regular singular point, this says irregular. But here, because they both are analytic at x equal to 0, we say this is a regular singular point.